Hi everyone, in this video we're going to look at the cross-entropy loss, which is the standard choice for single label multi-class problems. So you feed in raw logits from the final layer of your network along with integer class IDs as targets, and internally PyTorch applies log-softmax and negative log likelihood, and by default it averages the loss across your batch. So let's go over the input and target dimensions here carefully, since many PyTorch users, especially beginners, often get confused about the shapes expected by the cross-entropy loss. Really, it is one of the most common questions on the PyTorch forums. So this is the general shape of the logits and targets fed into the loss. On the left here, the logit shape is like batch size by class, and ... here depends on your task. On the right, the target shape, which is like just the batch size, and ... depends on your task. For example, here on the top, this can be, for example, used in sequence labeling tasks like named entity recognition, where, for example, the logits like batch size, class, and the sequence length, and the target is like batch size by sequence length. I have to say, even with LLMs, token level classifiers are still common in production for efficiency and control. At the bottom, for example, here in semantic segmentation, used when the model outputs an image-sized prediction. So each pixel receives C class path scores. So this is batch size, class, height, and width. The target is like batch size, height, and width. Height and width. We're actually going to see an example for this. So I'm going to remove this, and we're going to look at our first example, which I call the traffic sign image classifier. We are classifying if an image is a stop sign or a speed limit. We have the network, a logit, and also the target. Batch size is 2, class obviously is 2. So the top row is the score for the first image that we put into, that we fed into this network, and we got this scores. The bottom one is the scores of the second image. So these are the targets. From the targets, we know that the first image is really a stop sign. Okay, so the dimension is like batch size by class, and the target is like just the batch size. So let's compute the loss of the first image. Well, all you have to do is take the logits of the first image. We know that it is like the logits are like 2.0 and 0.5 here from here, and the target is 0. The cross entropy loss tells us to take the exponential of each logit. So for image 1, it's going to be e to the 2.0 divided by the summation of e of all of the values, and we're going to get this true class probability. Why e to the 2.0 at the top? Because it is the true class score, right? From the target, we know it is the true class score. When you do that, you get this probability, and to get the loss, all you have to do is take the negative log likelihood of that, and you are going to end up with this loss. For simplicity, I won't go into the full derivation of why we take the negative log likelihood. There are great resources that explain how this formula comes from the probability theory. Okay. However, PyTorch also provides an optional parameter called label smoothing, introduced in the paper Rethinking the Inception Architecture for Computer Vision. I'm going to put the link of that paper in the description. So this is the standard way of computing the loss, the cross entropy without any modifications. I'm going to show you that other way that I mentioned using label smoothing, which is this. Let's say we set that parameter to 0.1 and we recompute the loss for image 1. First, we need to compute the softmax probability. While we have already computed this for the true class, we need to repeat this process for the wrong class. So instead of E.2, we're going to put E.5. I will get the probability of 0.182. So this is the softmax probability. Then we need to compute the smooth target, which depends on this 0.1. Well, since there are two classes, the smoothing formula distributes 10%, 0.1 of the confidence evenly across all classes. The correct class gets 1 minus 0.1, this, and other classes, the other class gets 0.1, the remaining. Now to get the loss, now the loss is computed using the softened target from both classes. So it's going to be negative 0.1 this times the natural log of the true class probability plus 0.1 this times the natural log of the wrong class probability, and you get this loss. So with the label smoothing, the loss increases slightly from 0.201 to 0.351. This makes the model less overconfident and helps improve the training stability. In this video, we won't actually use this, the label smoothing. I just wanted to show you how it changes the computation behind the scenes. Okay, so we will be using the standard way of computing the cross entropy loss. Well, this is the loss of the first image. You can repeat the same process for the second image. So you're going to replace this logit with 0.1, 1.5 and the target of 1. And let's say you do that. You get, let's say, 0.220, take the average, and this is the batch loss. Okay, I think it is clear. Maybe I can remove these items here, and we're going to move to our second example. The road scene semantic segmentation. So our goal is to classify each pixel of the output of a model as either a car or a pedestrian. We have two classes, obviously. C is 2, N is 1 for simplicity. So this is the model's output of dimension NCHW. So we have one image, 2 channels, and the number of channels depends on the number of classes, and each channel is like has a height of 2 and a width of 1. Target is like NHW, kind of doesn't depend on the C. So this is the model's output for the semantic segmentation, and I just want to help you kind of understand the channels. So we have 2 channels, which depends on the number of classes. Let's say this is channel 1, channel 2. Okay, and let's make sense of that. In the first channel, the top 1.1 is the score that the top pixel belongs to the car class. While this 0.3 is the score that the same top pixel belongs to the pedestrian class. So this is like the back channel at the back, and the front one is this channel. Okay, so this is the score that top pixel belongs to the car class. This is the score that the same top pixel belongs to the pedestrian class. In other words, each pixel has 1 score per class, 1 from each channel. Okay, this minus 0.4 is the score that the bottom pixel belongs to the car class. This is the 0.7 is like the same bottom pixel belongs to the pedestrian class. Okay, so let's compute the loss quickly. The top pixel, we know the logit 1.2 and 0.3. We know the target here is 0. Well, we are really going to be repeating the same process, e to the true class codified by e to the all of the values, sum them up, and we do this division, we get this probability, we take the negative log likelihood of that probability, we get the loss. The same thing for the bottom pixel, you can repeat the same process. Right. Let's say you repeat the same process, you get 0.287, take the kind of average and you'll get the loss. So really this is it. It's really not that difficult, and there's going to be a Jupyter notebook for this tutorial. Thank you very much.